My name is Samantha, and I'm going to be discussing the NMR spectrum as well as some following NMR concepts. This is going to include the number of signals, the position of the signals on the NMR, integration of signals, and spin-spin coupling. So first, when I can tell that this is a NMR is because of the x-axis. It only goes up to 5, whether carbon you would see up in the hundreds. So first I'm going to take a look at the number of signals. So you can see here that there are 3 different types of signals. These are all representative of unique groups of hydrogens. So this signal right here and the first one is one, they all share one signal. This is another signal, and this is the third signal. We can actually represent these by HA, HB, and HG, showing that they're all separate signals. Next is going to be the position of the signals on the NMR spectrum. So first I'm going to estimate this one's about 1.3 ppm. This one's going to be around 2.2, and this last one's going to be around 4.1 ppm. So if you take a look at this graph provided, you can see that around 1.3, it's not going to be an amine, it's not going to be an alcohol, so we're going to assume that it's probably going to be part of an alkane, especially because we are looking at ethyl acetate. Next, we can see that around 2.2, again, it's not going to be amine, not going to be alcohol. We do have a carbonyl in ethyl acetate, so that's what I'm going to look for. There's no sign of any alkynes, no halides, and it wouldn't be part of an aromatic ring or any carbon double bonded to carbon. Lastly, we have one at around 4.1, which we can see is probably, again, not an alcohol, but sitting at the ether, alcohol, and ester peak. Because this compound is the ethyl acetate, which looks a little something like this, we know that we are going to be seeing this ester functional group. So we can sort of conclude that that's what we're going to be seeing on the NMR. So now that we have this, I'm just going to label what we see here. So HA, we said that was part of the alkanes. HB could be the carbonyl or a hydrogen that is close to a carbonyl causing the shift, and then HG, which we said what could have been the ester functional group. Next, we're looking at the integration of signals. So this, the 3H, 3H, and 2H, that's the number of hydrogens that share that unique signal. So if we draw out this molecule, we can see that if we expand a little bit, there are 3 hydrogens on this carbon, 2 hydrogens on this carbon, and another 3 hydrogens on this carbon. So if we take a look back at our hydrogen NMR, we can see that this carbon right here contains 3 hydrogens. This one contains 2 hydrogens, and this one contains 3 hydrogens again. So if we look at our NMR, we can see that at around 1.3 we have that alkane peak. So it would make sense that these H's right here, which all share the same signal, would be represented as the HA. It falls as an alkane, and it has 3 hydrogens, so that makes sense. If we go over to HB, that is what we think of as the carbonyl. It is around 2.2 ppm, like we said, and it says it has 3 hydrogens. So if we know that we've taken care of this alkane hydrogens, we can see that this is the only other group that contains 3 hydrogens, so we're going to label this as HB. Next, we see that this is the peak at 4.1 only has 2 hydrogens, so we can assume that these 2 hydrogens will share the same signal, and it can be HC. So we can further back up this claim by taking a look at the spin-spin coupling, which could give us an idea of what kind of hydrogens, or what hydrogens are going to be located adjacent to this carbon. So for example, just in a different color here, so if we take a look at this first signal right here, we can see that this is a triplet by 1, 2, 3 separate peaks inside this little complex. So using the equation for spin-spin coupling is n plus 1, n being the number of the adjacent hydrogens, we can see that 2 plus 1 equals 3, 3 being the number of peaks. So we know that there's going to be 2 adjacent hydrogens to this HA, to the HAs. So we can see here, this is the HA, and we're going to look for the hydrogens adjacent, and we can see that this is 2 hydrogens, and they do share the same signal. So we're saying that does look good. The second one, we're looking at HB, right? And since we know that 0 plus 1 equals 1, we're going to know that we know there's going to be 0 neighboring hydrogens. So if we take a look at this HB, look at the neighbor, and there's no hydrogens, so in that aspect we're good. Next, we're going to take a look at this HC, and so this HC again corresponds to this portion right here on the molecule, and we can see that there are 4 peaks, which are actually called quartet, I think, quartet, and so we know that 3 plus 1 equals to 4, which is the quartet. So we know there's going to be 3 neighboring hydrogens. We can see here that this is HC, and there are 3 neighboring hydrogens, which check out very nicely. In case I didn't say so, this is the triplet, this is actually a singlet, and this is the quartet, and these are all based on the amount of peaks. So those are the 4 different general NMR concepts, which include the number of signals, which we determined was 3 separate signals, the position of the signals, and what functional groups they corresponded to, what we would sort of see in the compound, as well as the integration of the signals. So it would either be the amount of hydrogens that shared the same signal, and then the spin-spin coupling theory, which uses the n plus 1 equation, and how we can use that to determine the adjacent hydrogens on the molecule. So now, using all the stuff that we just reviewed, we're going to go over this molecule aspirin, and this is what aspirin looks like. We can see that there is an ester, there's an aromatic compound, and there is a carboxylic acid. So we're going to see all those on the NMR and determine those through the position of signals as well. So first, I'm going to determine how many signals there are in the NMR, which will give me a good indication of how many unique hydrogens there are going to be. So this is 1 signal, which is located, I want to say, around 2.2, 2.1. Next, we're going to have 3 separate signals all around 8, which I'm going to say this one's 7.8, this next one's going to be 7.9, and then this next one is going to be around 8.2. And again, that is going to be signal number 2, signal number 3, and signal number 4. Lastly, we're going to have this one last signal at 5. It is at 11, which is a characteristic of a carboxylic acid. I'm jumping the gun a little bit, but this one's pretty easy to point out. It's usually pretty far to the left in the NMR, which is a really good indication that it is there. So we determined that there was 5 signals. We also determined the position of the signals, and I'm going to go into a little bit of detail about what functional groups we're going to see with these signals. So if you look over here, we had a bunch of signals over in the 8 region. It's not going to be an amide. We don't have a nitrogen in our compound. It could be part of the aromatic compound, as well as alkenes that we're going to see in the aromatic compound. So anything around 8, I usually chalk up to being an aromatic structure. So next, we're going to take a look at this peak around 2.2. So it's not going to be a amide again. It could be part of an alcohol, which we see in carboxylic acid. It could be another carbonyl compound that we see. Not going to be an alkyne, won't be a halide, and we've already sort of marked down aromatic compounds, so we can just sort of get rid of that one. So I'm going to say this could potentially be part of another carbonyl compound. What's interesting about this compound is that we do see a carbonyl here, but with this extra oxygen, it actually makes it an ester. And the reason why this signal is actually shifted upwards from where we would originally see it is due to chemical shifting by the aromatic compound, which is why this could be a little more upfield and could indicate an ester compound. So we're just gonna keep that in mind while we go through this. There are other ways, including the signal integration and more likely the spin-spin coupling, that will tell us more about the hydrogens involved. So looking at the signal integration, it's a little different because it's not telling us what signals we're seeing. So for example, for carboxylic acid, that one's pretty much a giveaway. We're going to have one hydrogen here. And although I'm not too sure about all the other hydrogens yet, you can infer that a higher signal means that there are more hydrogens that share the same unique signal. So I would assume that this signal would most likely be greater than one hydrogen. Not too sure about these ones, but since they're part of the ring, I can infer that more than one hydrogen on the ring must be sharing the same signal. So if we go to this molecule and we just sort of label the hydrogens that we have, this is going to be a carbon with 3 hydrogens attached. This is going to have 1 hydrogen, another hydrogen, third and a 4th hydrogen, and this is going to be our other hydrogen up here. Can't forget about the carboxylic acid. So I'm just going to go through and determine like signals. So first, right off the bat, you can tell that this carboxylic acid is going to be a signal in itself due to the hydrogen being the only one attached to that specific oxygen. If there was a second hydrogen attached, we would look at that being, a signal together, but there isn't. Next, we're going to take a look at these hydrogens over on this carbon. They're all attached to the same carbon, which is attached to another carbon. So I'm just going to make that its own signal. Now we're going to get into the aromatic ring. So since these hydrogens right here are both adjacent to each other and other hydrogens, I'm going to say that these two share a signal. So I'm going to give this one its own. Because this hydrogen is adjacent to an oxygen, and this one's adjacent to a hydrogen. This one is also an adjacent to an oxygen, but it's a double bond, so it's going to be a different signal. It's also bonded to different things. So this oxygen is bonded to a different functional group. So this has an OH, this has a CH3. So I'm going to give this one its own signal. So we can see that we have 5 signals here, which match with the 5 signals that we're getting on the NMR as well. So next we're going to try and use spin-spin coupling in order to determine which signal matches up to what we see on the compound. So right away we can see that this was the carboxylic acid. So I'm going to say that this was HA, working backwards a little here. So HA, using the n+1 rule, n being the number of adjacent hydrogens, we know that since it is a singlet, which corresponds to 1 peak, 0 plus 1 equals 1. This one being the peak, the number of peaks, this one again being n. So we know that there's going to be 0 adjacent hydrogens in this carboxylic acid. So if we look over, we can see that there is no hydrogen, so that is all set. Next we're going to move over here. And again, this is the one we weren't too sure about, but we do now know that it is most likely going to be that greater than one hydrogen that we talked about earlier, with the signal integration, because it is a larger peak. So we're looking at one that has more than one hydrogen. So it could either be here or here, but since we were looking at a carbonyl or ester, number 2 is the only one that really falls in that category. So I'm just going to label this one as HB. And we're going to see here it is a singlet, so same thing, it's not going to have any adjacent hydrogens, and you can see that there are no adjacent hydrogens, which works out really well. Sort of skipping through this, this is going to be looking at the aromatic. There are a bunch of multiplets, doublets of triplets of multiplets of all that stuff. So it's quite hard to see what exactly it is, but if you look here, we have 3 different signals within the aromatic ring, and that actually corresponds pretty good with what we have here. Knowing upfield and downfield shifting. Downfield shifting occurs with a decrease of shielding, so an atom next to a more electronegative group will have a decreased shielding due to that electronegative group stealing those electrons. So in this, I would most likely say that 5 would be more of the downfield. It's next to that carboxylic acid group, which is much stronger than the ester, and so I would put that one at HC, that most downfield shifted group. Next we have that other one, and since this last peak is actually much taller, I'm going to assume that this one is 3, so HD. It also makes sense considering that it is more upfield, which means it's away from electronegative groups, and it has increased electron shielding. So that leaves HE, which I'm going to assign for 4. So using all these 4 different general NMR ideas, we're able to take a look at a compound and see what fits and how to determine hydrogen interactions through this NMR.